Hello everyone. In the beginning of the class, let us see new announcements. Okay, the first new announcement is April 26th, 2022. Class videos uploaded. Hello everyone. I have uploaded class videos of April 26, 2022 to YouTube. Their URLs are this, and this. Okay, best regards, Wei Jin. Okay, the next new announcement is the slides of Chapter 2 has been updated, version 2022-0428. Hello everyone, I have uploaded the latest version of slides of Chapter 2 to eCourse2 website. The location and the file name are eCourse2 website, wireless communications and machine learning. Course content, slides, Chapter 2 slides 2022, 2022-0428 .pdf. Best regards, Wei Jin. Okay, the third new announcement is the handout of Chapter 2 has been updated, version 2022-0428. Hello everyone, I have uploaded the latest version of the handout of Chapter 2 to eCourse2 website. The location and the file name are eCourse2 website, wireless communications and machine learning. Course content, handouts, Chapter 2 handout 2022-0428 .pdf. Best regards, Wei Jin. Okay, next let us look at the progress of the last class. In the last class, we have taught to Chapter 2 slides, page 47.3. Okay, unfinished. So please open the slides of Chapter 2 and please turn to page 47. Okay. So point 3, with a table-based algorithm, referred to this way because it estimates the Q values for each possible pair. SIAI. Okay, what does it mean? Okay, it means a table-based algorithm. Okay, so SI is the state of the secondary user I, and AI is the action taken by secondary user I, such as algorithm 1. Okay, let us go to algorithm 1. Okay, we have introduced algorithm 1 in the last class. Okay, algorithm 1 is the basic strategy learning based on standard Q-learning. Okay, it is a 10-line algorithm. Okay, one reason for the slow convergence is that it estimates, okay, it means the algorithm 1, each Q value for each possible pair of a state and an action through a stochastic gradient descent method. Okay, what is stochastic gradient descent? Okay, let us see the handout. Okay, so let me search for stochastic. Okay, next. Okay, next. Okay, here. Okay, it is page 47, problem 2. What is stochastic gradient descent? Solution: stochastic gradient descent, often abbreviated SGD, is an iterative method for optimizing an objective function with suitable smoothness properties. For example, differentiable or subdifferentiable. Okay, what is subdifferentiable? Okay, let us see problem 3. What is subdifferentiable? Okay, if only differentiable, I think you have already learned it in the course calculus when you were a freshman. Okay, solution: a function f is called subdifferentiable at x if there exists at least one subgradient at x. Okay, so problem 4, what is a subgradient? Okay, solution: if f u2r. Okay, what does this mean? Okay, f and column and u and right arrow and r. Okay, f means the function, the name of the function, and u is the domain of the function, and r is the range of the function, and r denote the set which contains all real numbers. Okay, if fu2r is a real valued convex function defined on a convex open set. Okay, we have defined what is a convex function. Okay, if you forget it, please review the handout. Then what is a convex open set? Okay, let us see problem 5. What is a convex open set? Solution: a convex open set is a set which is both a convex set and an open set. Okay. Then problem 6. What is a convex set? Okay, solution: in geometry, a subset of a Euclidean space, or more generally, an affine space. Okay, what is an affine space? Okay, excuse me. Okay, problem 7. What is an affine space? Solution: in mathematics, an affine space is a geometric structure that generalizes some of the properties of Euclidean spaces in such a way that these are independent of the concepts of distance and measure of angles, keeping only the properties related to parallelism and the ratio of lengths for parallel line segments. Please see figure 16. Okay, let us see figure 16. Okay, this figure. Okay, so I need to zoom in it. Okay, so let me try. Okay, so let me enlarge it. Okay. Okay, figure 16 in R3. Okay, what does R to the power of 3 mean? Okay, it means the three-dimensional real vector space. The upper plane in blue, P2. Okay, P2 is here. It is this plane. Okay, blue plane is not a vector subspace. Since the vector 0 is not in P2. Okay, because the vector 0 is here. Okay, it is not in P2. Okay, recall the definition of a vector space. Okay, one of the condition is that the vector 0 should be in a vector subspace, and A plus B is not in P2. Okay, let us see. Okay, A is in P2 here, and B is in P2 here, but A plus B, okay, vector A plus vector B is not in P2. Okay, according to the definition of the vector subspace, if vector A is in the vector subspace and vector B is also in the vector subspace, then A plus B must be also in the vector subspace. Okay, it is an affine subspace. Its direction is the lower green plane P1. Okay, this is the plane P1. Okay, this plane. Okay, P1, which is a vector subspace. Okay. Okay, you can see that the plane P1 is actually the xy plane. Although vector A and vector B are in P2, okay, here, vector A and vector B are in P2. Their difference is a displacement vector. Okay, here, for example, A minus B, vector A minus SB, vector B is this vector. Okay, and this vector is in P1. Okay, here, but not in P2, which does not belong to P2, but belongs to vector space P1. Okay, let us go back to the affine space. Okay, figure 16. Okay, so affine space. Let us go to the first affine space. Okay, an affine space over the reals. Okay, affine space. Over the reals. Okay, is convex if given any 2 points in the subset. The subset contains the whole line segment that joins them. Okay, please see figures 14 and 15. Okay, let us see figure 14 first. Okay, figure 14 is an illustration of a convex set which looks somewhat like a deformed circle. Okay, this is a convex set. The line segment illustrated in black above. Okay, it is the line segment. Okay. Joining points X and Y lies completely within the set. Okay, you can see that this line segment joined the point X and point Y. Okay, and this line segment completely lies in this set. okay, illustrated in green. Okay, this set is in green. Okay, since this is true for any potential locations of any 2 points within the above set, the set is convex. Okay, you can try, okay, arbitrarily choose 2 different points in this green set and connect them. Okay, then the line segment connect the 2 points are also completely lies in this green set. So this green set is a convex set. Okay, let us go back to the convex set. Okay, then let us see figure 15. Okay, so figure 15 is an illustration of a non-convex set. Okay, let us see. Okay, this is a non-convex set. And why? Okay, illustrated by the above line segment, whereby it changes from the black color to the red color. Okay, because we choose 2 different points x and y in this green set, and joined x and y using a line segment, you can see that the black part of this segment lies in this green set, but the red part of this segment is outside of this green set. Okay, so it's amplifying why this above set illustrated in green is non-convex. Okay, so we can know that this green set is not a convex set. Okay, let us go back to the problem convex set. Okay, so convex set comes from here. Okay, and what is an open set? Okay, let us go to problem 8. What is an open set? Okay, open set. Okay, open set. Okay, what is an open set? Okay. Okay, solution. In mathematics, open sets are a generalization of open intervals in the real line. In a metric space, that is, when a distance function is defined, open sets are the sets that, with every point P, contain all points that are sufficiently near to P. Okay, that is, all points whose distance to P is less than some value depending on P. Okay, please see figure 17. Okay, let us see figure 17. Excuse me. Okay, figure 17 is an example. The blue circle represents the set of points x, y, satisfying x squared plus y squared is equal to r squared. Okay, we can see that here is the okay, let me zoom in it. Oh, it is too it is okay. Okay, the blue circle represents the set of points xr satisfying x squared plus y squared is equal to r squared. Of course, r is a positive constant. Okay, and then let us continue. Okay, the red disk represents the set of points x, y satisfying x squared plus y squared is smaller than r squared. Okay, let us see. Okay, this red disk represents the set of points x, y satisfying x squared plus y squared, which is smaller than r squared. Okay, so the red set is an open set, the blue set is its boundary set, and the union of the red and blue sets is a closed set. Okay, so we can see that the red set is an open set. Okay, and the blue set is its boundary set, and the union of the red and blue sets is a closed set. Okay, we will introduce what is a closed set later. Okay, let us go back to the open set. Okay, so let us see the formal definition of an open set. A subset U of the Euclidean n space R to the power of n. Okay, that is, it is the n-dimensional real vector space. Is open if for every point x in U there exists a positive real number epsilon depending on x, such that a point in R to the power of n belongs to U as soon as its Euclidean distance from x is smaller than epsilon. Okay, equivalently, a subset U of R to the power of n is open if every point in U is the center of an open ball contained in U. Okay, what is an open ball? Okay, before explaining what is an open ball, let us see problem 9 first. Problem 9, what is a closed set? Okay, solution. In geometry, topology, and related branches of mathematics. Okay, a closed set is a set whose complement is an open set. Okay, then let us see, okay, problem 10. What is an open ball? Okay, solution. In mathematics, a ball is the solid figure bounded by a sphere. It is also called a solid sphere. Okay, it may be a closed ball including the boundary points that constitute the sphere, or an open ball excluding them. Okay, in Euclidean space, in Euclidean n space, that is the n-dimensional real vector space, an open n ball of radius r and center x is the set of all points of distance less than r from x. A closed n ball of radius r is the set of all points of distance less than or equal to r away from x. Okay, so we have explained what is an open ball. Okay, it comes from the problem of open sets. Okay, so page up, and page up. Okay, and open set comes from the problem of what is a convex open set. And let us go back to the first time that convex open set appears. Okay, it is 25 minutes. Let us take a break.